Brought to you by the Astro Youth House chapter from STEM Arts Lab, Space on Earth is a student-led podcast that inspires listeners who are curious about space to explore the wonders of the universe through the voices of young thinkers, creators, and dreamers.
Each episode blends personal curiosity with scientific discovery, from the mysterious depths of black holes to the practical impacts of space on Earth, like GPS, climate science, and medicine.
Hosted by STEM Arts students from Taos, New Mexico, this podcast draws connections between space, art, and science, how these things all impact us here on Earth, and their meaning to humanity.
You'll hear raw, insightful conversations about topics like light pollution, the overview effect, lunar exploration, and the societal impact of the space race.
Whether you're into exoplanets, dark energy, or just stargazing from your backyard, Space on Earth makes space personal, accessible, and inspiring. We believe that space isn't just for astronauts and scientists, it's for everyone.
Join us on this adventure as we explore the cosmos from Earth, one story at a time.
Special thanks to the Lore Foundation for helping launch this podcast.
Hi everybody, welcome back to another episode of Space on Earth. I'm Taylor.
I'm Hattie Rose.
I'm Tulsi.
I'm Wyatt.
So today we're going to go over the sun, its life cycles, and how it affects us on Earth, its relation to rockets, and a lot more. So let's start with some facts about the sun. The sun is classified as a G-type main sequence star, or a G2V, which astronomers also call a yellow dwarf. It belongs to the group known as population 1 stars, younger stars that are richer in heavy elements compared to the older metal-poor population 2 stars. In terms of size, the sun is really big, it's enormous. It's about 1.39 million kilometers in diameter. That is 109 times wider than Earth, and it contains 99.86% of all the mass in our entire solar system. It's also really old. The sun formed around 4.6 billion years ago, and it's currently about halfway through its 10 billion year life cycle. So in roughly 5 billion years, it'll run out of hydrogen fuel in its core, and when that happens, it'll expand into a red giant, shed its outer layers, and eventually shrink down into a dense white dwarf, surrounded by a glowing shell of gas known as planetary nebula. But how is the sun different from the planets that orbit it? First, the sun is a star, not a planet, and that changes everything about its nature and role in the solar system. Unlike planets, the sun generates its own energy through nuclear fusion, turning hydrogen into helium and producing light and heat in the process. Planets, on the other hand, can only absorb and reflect that energy. The sun is made entirely of hot plasma and gas, while planets can be rocky like Earth, or made of gas and ice like Jupiter and Neptune. All planets orbit the sun due to its immense gravity, and that's what keeps every other body in the solar system in motion. Another key difference is that the sun has no solid surface, no seasons, and no weather in the way that we experience it on Earth. Instead, it has powerful magnetic activity that produces sunspots, solar flares, and coronal mass ejections, events that simply don't happen on planets. In short, the planets are passive worlds dependent on the sun for light, heat, and even the ability to sustain life like on Earth. The sun is the true engine of our solar system, and without it, all planets would be cold, dark, and adrift in space. There's also a lot of research related to rockets, which Wyatt is an expert in. So do you want to talk a little bit about that regarding the sun?
Yes, I would. The first man-made satellites were put into Earth's orbit back in 1958. We've sent plenty of probes and scientific experiments to examine and learn about our sun. And I got a list of the 3 most important missions that we have designed, built, and sent to the sun so far. With first, that being the Parker Solar Probe, which was built by NASA JPL. It was launched back in August of 2018. It flew on the ULA Delta IV Heavy, which is now retired, sadly. It was a beautiful rocket. The main goals of the Parker Solar Probe were to fly closer to the sun than any previous spacecraft to directly sample the near-sun environment, and also measure the structure and dynamics of the solar corona in the origins of solar wind, and to also determine how the sun's magnetic field drives energetic particle and space weather. Some of those important achievements of the Parker Solar Probe: it got closer to the sun than any human-made object ever, but not close enough for it to get destroyed by the heat of the sun. So it's crazy engineering that we can build something to basically, in a way, dive through the sun. Not entirely, but it's became the fastest man-made object ever. So that's an achievement too. Next is the Solar and Heliospheric Observatory, which was a joint mission between the European Space Agency and NASA. It was launched on December 2nd, 1995 on a Atlas II rocket. The main goals of the SOHO, that's the abbreviation for it, were to provide continuous long-term observations of the sun across many wavelengths to study structure, dynamics, and the solar interior of the sun, and also to monitor the solar corona for CMEs or coronal mass ejections for scientific study and space weather forecasting, and to also just observe the heliosphere in solar wind conditions at the Sun-Earth Lagrange 1 point. So basically, a Lagrange point is the 1 point in between two orbital bodies where each body pulls on the payload equally. So it's basically stuck in between Earth and the sun. So like it just doesn't move. It's synchronized with the Earth's rotation around the sun. And it's really cool. Moving on to the Solar Orbiter, just a ESA mission with a little help from NASA. It was launched on February 10th, back in 2020. It was launched on a ULA Atlas V. Some of the objectives for the Solar Orbiter were to get close to the sun and observe the solar poles, and to also make measurements to connect phenomenon on the sun's surface to conditions in the inner heliosphere, and to study how the solar wind is formed and how magnetic structures propagate outward. Tulsi, would you like to talk about how the sun affects Earth?
Yeah, I would actually. So there's a couple ways that the sun affects Earth. And the first one is aurora borealis. So aurora borealis occurs when charged particles from the solar wind interact with Earth's magnetic field. So it's usually seen in the far northern or southern parts of the world because the magnetic field tunnels particles toward the magnetic poles, which are also the poles of the Earth and not really near the equator. So basically, how auroras happen is that the sun is constantly releasing energy in particles into space, and sometimes those particles form solar winds. And when they hit the poles or the magnetic field around the poles in that area, energetic collisions with atoms in the upper atmosphere produce visible light. So within this magnetic field of the Earth, there's the ozone layer, and the ozone layer protects life by absorbing UVB and UVC. And solar storms and winds can temporarily alter the ozone's chemistry and the upper atmosphere, which creates reactive molecules and slowly actually wears down the ozone, which is bad. There are also storms called geomagnetic storms. And so geomagnetic storms are triggered by solar flares, which can disturb satellites, power grids, and navigation systems. And I don't know if you guys have ever heard of the Harrington event of 1859, which caused telegraph wires and auroras as far south as the Caribbean, which isn't normally very common at all. And that was a geometric storm. So if big enough, they can do a lot of damage and alter the magnetic system a lot. Also, just like there are different kinds of solar storms, there are also different kinds of UV. And UV, or ultraviolet light, is categorized into UVA, UVB, and UVC. So UVA penetrates deep into your skin and causes aging. UVB causes sunburns and is linked to skin cancer. And UVC is mostly blocked by the ozone layer. But even though the Earth has an ozone layer, stars like the sun don't.
and their life cycle is different from the planets too. So, Taylor, do you want to talk about that?
Yeah, so totally. And another thing about our sun is that there's definitely a lot of unique aspects to it when we compare it to other stars. So, obviously the most noticeable difference is how close our sun is to us. So it's closer to Earth, like more than any other star. And so because it's that close, we see it so much larger and brighter. And, that's one of the obvious differences. But when you're thinking about how many stars there are in a larger picture, it's pretty amazing that like we have ours. And then, like we said earlier, the sun is a G-type main sequence star. And so compared to other stars, it's brighter than around 90% of most stars, but it's also cooler and dimmer than some other like blue giants or supergiant stars. Another thing to note is that our sun is not in a star cluster. So ours is completely standalone, and we call that a solitary star. And it's actually a bit unusual because many stars are born in clusters or binary systems, which means that you have two or more stars orbiting each other. And our sun has a really large planetary system. So we have a complex solar system of 8 planets and dozens of moons, countless asteroids, comets, and a lot of stars do have exoplanets, but they don't have maybe as much planets, or it's not stable or diverse as our solar system. So, one big thing is that it's made out of the same stuff. Our sun is mostly composed of hydrogen, so about 74% hydrogen and about 24% helium. Most stars have the same makeup. And these elements fuel nuclear fusion in the core of the sun, which is the same process that powers other stars. And like other main sequence stars, that fusion is turning hydrogen into helium inside of the sun's core. And so that releases energy as light and heat, just like any other star. And that's how we get light and heat to have life on Earth. Also, our sun creates elements that we see throughout our solar system, like carbon and oxygen, during their lives and deaths. And both of those elements are really crucial to life on Earth. And it emits a full spectrum of light. So, not just the visible light that we can see, which is, just what you see when you're looking around, but our sun also emits ultraviolet and infrared light, just like any other star. And we can use those other types of light to take more photos and get more data in different ways. And also, this spectrum of color and different wavelengths of light, it can help astronomers classify our sun and learn about its temperature and composition, which is also how we study other stars. And, most importantly, it's a part of the galaxy that we're all in. And there's billions of other stars. And so when you think about it, it's pretty incredible that like we have our own special sun, but it's so different and so similar. Thank you so much, as always, for supporting and listening to our show. We are so grateful to have your guys' support. Also, like always, if you have any questions, curiosities, or ideas for future episodes, feel free to reach out. We always love to hear from you guys, and we'll cover it in a future episode. I'm Taylor.
I'm Hattie Rose.
I'm Tulsi.
And I'm Wyatt.
And we'll see you guys next time. Bye.
Thank you.